Welcome to the Crazy Hat Chemist. So another video here on thermochemistry. So let's get moving. Bam! So today we're doing thermochemistry calculation number three. What is the temperature of water when 120.0 gram iron weight, specific heat capacity of 0.473 joules per gram degree Celsius, is heated to 125 degrees Celsius and placed in a calorimeter containing 225 grams of water at 25.0 degrees Celsius? So we first need to, of course, know the equation in which we are using. Okay, so one very important equation is this one right here. That is the Q, the heat of the metal, plus the heat of the water is equal to 0. Okay, the other way of writing this is Q of metal is equal to negative Q of water. Okay, so that means that the heat of the metal is transferred to the water, and the water absorbs that heat. But whatever heat is transferred from the metal to the water is equal but opposite in sign. That's why they sum up to the 0. So that's a very important concept here. So this is actually thermal equilibrium when they are summing up to 0. They're the same value, just opposite in sign. Okay, then we are using this equation, of course, which is Q equals mc delta T, but the delta T I've transferred into the TF minus TI. So I got Q is equal to mCp times TF minus TI. So this Q, which is going to be mc TF minus TI, is going to go into the metal, and then it's also going to go into the water. So it's going to be substituted into the Q of metal and the Q of the water. So let's write out that equation. So I'm going to have Q of metal, which is going to be mc TF minus TI, plus Q of water, which is mc TF minus TI, is equal to 0. So that's going to be right here, right now. Okay, so I got M for the metal, and notice that I've included the lower M's for the metals and the W's for the waters. So that's M times Cp for the metal times T final for the metal minus T initial for the metal plus the mass of the water times the specific heat capacity for the water times the temperature final for the water minus the temperature initial for the water. This is summing up to, of course, 0. Equals 0. So now we're going to figure out where these numbers belong in this equation from that information. So this 120 gram iron weight, that's going to be the mass of the metal. That's going to go right into there. My specific heat capacity for the metal is 0.473 joules per gram degree Celsius. Okay, my initial temperature for the metal is 125 because it was heated to 125. The mass of the water is 225 grams. The specific heat capacity is a tabled value, and you should actually have this one memorized. It's 4.184 joules per gram degree Celsius. It's the same joules per gram degree Celsius for the conversion between joules and calories. Okay, and then the initial temperature of the water is 25.0 degrees Celsius. So, I'm missing something here, and that is, what is the temperature of the water when? So this is very important that you understand this, okay? And that I am solving for the final temperature for both the water and subsequently for the metal, because something is very important here. The final temperature for the metal and the water is the same because you are reaching thermal equilibrium. That means all the heat has transferred from the metal into the water, since the metal is the hotter object in this case. If the water were the hotter object, then it would be the opposite way around. Okay, hopefully you got that. So now what we're going to do is we're going to plug in these values into that equation, bam, just like that. So you should see the 120 gram weight for the iron. You got 0.473 joules per gram degree Celsius for the specific heat capacity. We got TF, which we're solving for, minus the 125 degrees Celsius, that's the initial temperature of the metal, plus the 225 grams of water, and times the 4.184 joules per gram degree Celsius, that's the specific heat capacity for water, times the final temperature, which we're solving for the water, minus the 25 degrees Celsius, which is the initial temperature of the water, and this all sums up to equal 0. Okay? All right, so this is what we're going to do mathematically. We're going to multiply the mass and the specific heat capacity, and then we're going to distribute that over the TF and the 125 in this case. We're going to do the same thing to the other portion here. We're going to multiply the mass times the specific heat and then distribute that number times the temperature of TF, which is my unknown, and the 25. Paying particular care to the negative sign in between the TF and the minus 125 and the TF and the minus 25. Okay, so I want you to pause the video here after you do that mathematical manipulation, then restart the video to make sure that you're on the same page as me. All right, here we go. Keep on going. So this is what I get when I multiply it out here. So the 120 times the 0.473, that's 56.76. Then I have replaced the TF with an X, because that's the variable that we all like to see. So and then that's X minus 125. Plus the 941.4, that is the product of the 225 and the 4.184. And then we got X in place of the TF, minus the 25 equals 0. So we're going to distribute the 56.76 with the X and the negative 125, and the 941.4 with the X and the negative 25. And that's what we're going to get right here. Now you should see this. We have some X terms, we have some non-X terms. We're going to combine our X terms and we're going to combine our non-X terms. Then we're going to move our non-X terms to one side and our X terms to the other side. Doesn't really matter which side you do, but you do have to combine the X terms and combine the non-X terms and separate them out on different sides. And we're doing that intermediate step right there. What I've done is I've combined the X terms and combined the non-X terms. Now I'm going to move that non-X term to the other side. That's probably the simplest thing to do. That way you don't deal with that negative sign. So we're going to add 30,630 to both sides, and that's what I get right there. Now I have a coefficient in front of the X that is 998.16. I'm going to divide both sides by that coefficient of 998.16, and then I'm going to get this number. Okay, so X is equal to 30.6864. Now I'm going to ask myself, how many significant figures do I need to have in this problem? I'm going to go back to the original numbers that were given in this problem. And the least number of significant figures that I have here are 3. So I'm going to have 3 significant figures. So I need to round this number to 3 significant figures. So that's going to be a 30.68. I'm rounding with that 8, and 8 is 5 or greater. I'm going to add 1 to the preceding digit, which is the 6. That 6 is going to be becoming a 7. I'm going to put the units on here to make sure that I have the correct set of units for a temperature, since this is a temperature and it was degrees Celsius before. So I'm going to pop that on there here. So here is my number, rounded correctly with the correct set of units. I got 30.7 degrees Celsius. And then I'm going to ask myself, does this number make sense? Okay, so I have a 120 gram iron weight and it's heated to 125 degrees Celsius. I got 225 grams of water and it's at 25 degrees Celsius. So numbers that certainly would not make sense would be any number that is greater than 125 or any number that is less than 25. Okay, so it cannot be hotter than the metal was initially, and it cannot be cooler than the water was initially. It has to be some value in between. And it is certainly not a 50-50 mixture of the two. So you're not adding the 125 and the 25, adding them up and dividing by 2. It really is dependent on the mass and specific heat of the metal and the mass and the specific heat of the water. That's what's very important here, and that's why that 30.7 is not exactly in between. In fact, if you look at these numbers a little bit more, you should see that the mass of the metal is the mass of the water is greater and the specific heat of the water is greater. So therefore, this value should be closer to the 25, that is the initial temperature of the water, than it should be towards the 125, the initial temperature of the metal. Hopefully that concept makes sense, because you've got to make sure that you look at your numbers and ask yourself, does this number make sense mathematically and for the problem? Because it's just not a math problem, it is a chemistry problem, which is an applied math problem. Okay, I hope you enjoyed that video, and I got a great hat for you here, and I think it's Taco Tuesday today. If you like that video, give me a thumbs up, subscribe to my YouTube channel, find my website. I got all my videos on my website ready to rock and roll, so you can get all your chemistry knowledge for both honors and AP right on my website. I'll see you next time for more videos. Bye for now.